Okay, what we have here is an example of how deceptively complicated or deceptively simple integrals can look, but yet require some really crazy techniques, and some knowledge of trigonometry more often than not helps a lot with integration. So for starters, if I had this problem where I had to find a definite integral from square root of 2 to 2 of this function, I would certainly go straight to technology. Wolfram will do that for us and give us an exact result and a decimal approximation, and it'll even show us step-by-step how to do it. The TI graphing calculator will give us at least the value of the definite integral in decimal form, which is nice. Yeah, I was just going to say 0.259. Yeah, there it is. And the other thing, oh yeah, I was going to say we also have Desmos is another option that we have to check our answers here. So getting the answer isn't really a problem if we have access to technology, but what if we were trying to understand mathematical methods? How would we do this? Well, it turns out that, as far as IB is concerned, if you're studying for IB, if you're going to have a substitution where there's some sort of random, like, where did you ever come up with that? Usually IB will guide you. They'll say, using the substitution x equals the secant of theta, show that, and they'll give you the result that they're looking for. So don't worry too much about having some sort of divine insight to be able to know what x was supposed to be. However, suffice it to say that when I see x squared minus 1 and I think about secant squared minus 1, it makes me think about some other trig things that I've seen before. So here's how the integral is going to take place. The first thing I need to do is differentiate my x on both sides, so now I could have dx in terms of d theta. It doesn't look like this is going to help at all, because now it says dx is equal to sine theta over cosine squared theta d theta, which is just a hot mess. But I'm going to stick with this, because here we have the square root of 2 was my original x boundary, and I'm going to solve that for theta to get that theta is pi over 4. So when x is the square root of 2, with my u substitution, it becomes theta equals pi over 4. Same thing when x is 2. Means the cosine of theta is a half, which means pi over 3 was my angle. And so now, with all of this in place, my x is equal to the secant of theta. My boundaries have been changed, so all I have to do is change my boundaries, as shown. Change the x squared minus 1 into the secant squared theta minus 1. And that's going to be to the negative 3 halves. Looks like I forgot to write that over here. And then we also have, you've got this hot mess over here where dx is equal to, look at all that stuff. So I'm going to take what it was at dx and replace it with all that stuff. Again, it looks terrible. But let's write it all down and take a deep breath and see if we can actually follow what's happening now. What's happening now is this secant squared minus 1, if you remember correctly, is one of the Pythagorean identities and translates directly into the tangent squared of theta to the negative 3 halves. And now we have sine of theta over cosine squared theta, which, if we played with that a little bit, we would actually see that the tangent squared of theta is to the negative 3 halves is really the... what we're going to do basically is we're going to apply the exponent, so the tangent squared, so the second power times the negative 3 halves power gives us a negative 3 power. So the negative, we're going to take the reciprocal of tangent sine over cosine, and becomes cosine over sine, and then the cube is also there, because again, 2 times 3 halves is 3, so we're basically making this tangent cubed. Then we're going to flip it over and make it cotangent cubed, and then we're going to turn cotangent into cosines and sines. A lot of trig identities going in there. But as you can see now, one of these sines divides with one of those, 2 of these cosines divides with one of those, and we get a really nice u substitutionable exercise. So now I'm going to go do another u substitution where u is the sine of theta, change my boundaries again. But look at how nice this is. It's easy to integrate. and because it's a definite integral, I'm able to put in my new boundaries instead of having to go back and figure out what those boundaries were, given the fact that I substituted twice. So I've showed you some videos and some content in the past that show some really straightforward, just like this is what U substitution is. I just want you to understand that for high-level math and IB, you might get something really simple like that, but usually it'll be embedded within some other interesting problem. However, they might give you a problem like this, which again, deceptively simple looking. They'll guide you into what substitution they want you to make, and they'll send you on this long trail of tears until you get the target. So this is a great way for the IB people to assess what you've learned in mathematics, because it requires, as you can see, quite a lot of fundamentals in order to be able to be adept all the way through this process. So anyway, I hope that's helpful. Thanks for watching.